Yep.
Perfect. And the theory book of Max Planck in quantum physics in Germany. When you have been still there, we met in Stuttgart.
Yep.
And I'm looking forward to the talk about quantum topological data analysis.
Thank you very much.
Thank you.
It's an absolute pleasure to be here. I do understand why you come each year.
Is it loud enough?
Yeah, can you hear me? Yeah.
Your speech is not,
I can't hear.
They do not hear you. They do not hear you. Okay, so there's a mutual non-communication. Symmetry.
Okay.
Out of the home door. Oh, English.
Muss ich was tun? Ah, it's okay.
Oh, so I am audible, right? It's fine. Okay, very good. Right. I have no clue what I wanted to say, but let's go back to business, which is talking about quantum topological data analysis. And I mean, this is a symposium on service-oriented computing. So, just out of curiosity, how many of you actually work in quantum computing? Can I see a bit of show of hands? How many of you are not familiar at all with quantum algorithms? At all? Like you've seen? Okay. I apologize to some of you, because I will go a little bit into quantum algorithms, because what I will talk about is quite cool, and it's actually explainable. I can actually explain the things if you know the basics of quantum computing, and if you don't, the point of this is to talk about it later over Uzo, and it becomes much more intelligible for some goal. So yeah, so the topic is quantum topological data analysis. Please interrupt, of course. But I want to start the talk with a deeper motivation that I really have. So this is Google Ngrams, and I googled quantum machine learning, and you see here a rapid growth of the popularity of the term starting around 2012. And if you know your quantum machine learning, you kind of know which papers prompted this. This was Seth Lloyd business. It started here and it's become, it diverges. It goes like to infinity. It's like every word on the internet is now quantum machine learning. In the case you didn't know, we should be thinking about top 10 quantum machine learning companies. You should immediately be buying stock. The next big thing, of course, quantum machine learning, and I know you're all doing it because obviously it's the most important thing in the universe. And I have to say I love quantum machine learning. I've been in the field since 2013, so now close to 10 years. And I love it, but these people love it more than I do. I'm a little bit confused as to why this is really so popular. So if you start reading quantum machine learning literature, you can kind of understand what might be the reason. The reason is because there seems to be evidence or belief, or more precisely hope, that quantum computers could speed up conventional machine learning methods. So some people believe that maybe, you know, instead of melting the polar caps by training our deep neural networks, we could save the environment by training them on a quantum computer. Even though I have to tell you, there's no evidence for that. We don't know that quantum computers can do that. Other people believe that quantum computing can offer completely new ways of doing machine learning. So this is maybe to echo what Frank talked about in the morning. It's not just about speed-ups, right? It could be about enhancing precision, accuracy, and so on. Even though, as I'll argue over Uzo, it can be argued that it's the same thing. But at least morally, these two things are a little bit different. So different models inspired by quantum information and simply speed-ups of classically specified models that have been identified. Right? So this is what you're going to read about. Of course, this is super and amazing. And there's the folklore that if there's any place where these quantum methods are really going to give classical methods a run for their money, it's going to be when the data comes from a genuinely quantum system. Right? That somehow sounds plausible, right? If you're going to use a quantum computer, you want to use it for quantum things. That's the place where it should work, right? And for everything else, we might be less sure. But I would like to tell you that, in fact, even this is not clear. Right, so I'm going to go very pessimistic for a moment, but then I'm going to become optimistic towards the end. So the two questions that I want to discuss is whether there are useful data processing tasks which allow for big speedups. Big here is emphasized because I really mean something which is more than a polynomial speedup. I will not be considering things like using Grover search to get a small quadratic speedup over classical techniques for practical reasons, again, which I can defer for a later conversation. And the second question, which I will not have a chance to talk about, but I want to tell you that it's very important, whether they're important classically hard yet quantumly easy learning tasks, like fundamental learning problems which can give us a separation between classical and quantum machine learning. So these are the two main questions. And today I will talk about the first one, whether or not we have super polynomial speedups in uncontroversially useful machine learning models. Yeah? So it's called motivation so far so good. Yeah? Maybe one thing that I should add, especially in this community, I'm putting the hat of the worst skeptic you can find. So the person who only cares about mathematical provable claims, because we don't have large quantum computers, I cannot convince you that they're useful yet. So the only thing I can argue is on the basis of theory, right? Even though I think we all hope that quantum computers are going to go way beyond that when they're large in terms of their business. Okay, so let's start with the idea of where quantum computing could help. Well, I think the story of quantum machine learning starts, let's say the second generation story starts with the idea that we can represent quantum states on a classical device, but the amount of storage we need seems to be exponential in the number of subsystems of the quantum system. So you have n qubits, you want to write down the generic quantum state of n qubits. It seems you need to use 2 to the n complex numbers, called quantum amplitudes, to fully specify it. And then, of course, you can spin the story around. If you give me a capital n-dimensional real value vector or complex value vector, well, ostensibly I can store it in just log n many qubits by storing really each one of these values into the amplitude, subject to 1 degree of freedom that I'll lose in that the quantum state has to be constrained in terms of its norm. So it looks like an exponential scale. That's what it feels like. N dimensions log n qubits, and in fact it turns out that everything else that we do in quantum computing can be understood verbatim as linear algebra. I prepare the quantum state in this quantum system in this state, so it's an n capital n dimensional vector. I do quantum operations on it, and everything that happens is nothing but large matrices being applied onto this vector. But note, my way of doing it is not scaling with capital N, it's only scaling with log n. Like each individual single qubit gate that I'm applying is actually being a huge matrix applied to the system. So the idea was, well, can I not really use this to compute linear algebra very efficiently? And around 2008, actually 2007, came out the now famous HHL, Hasidim, Heron, Lloyd paper on how to solve linear systems using quantum computers, which suggests such a super polynomial improvement, which had a lot of fine print. You couldn't really solve large systems of equations efficiently because you had to somehow prepare these states. I didn't tell you how to prepare a quantum system in this state. Then if I wanted to do matrix inversion, I would have to worry about the condition numbers of the system that I'm inverting. I would have to worry about the error scaling and the fact that even though I might have capital and quantum amplitudes, when I measure the system by the level bound, I get at most log n bits out. So whatever I'm doing better not require me to recover the entire vector, because this is out of the question for the quantum system. But funnily enough, in much of data analysis, what we really do is linear algebra. And in much of data analysis, we don't really care about errors that much. So, you know, if you think about GPUs and TPUs in particular, 8 to 16-bit precision seems to be enough for everything that we want to do. Readout and what we want to compute out of this thing, sometimes it's just a single bit. If we're doing a classification problem, it's a 0 or a 1. That's all we care about. So it turns out that in the machine learning context, somehow all of this fine print is less painful. It seems that we have ways of getting it to work. By getting it to work, I mean really recover this exponential speed up over classical methods. And we had a bunch of proposals, doing recommender system, principal component analysis, support vector machines, frigging, you name it, people have done it in this particular framework. And it was working fantastically up until 2018, when this meme came out. Maybe this was before you were interested in quantum computing. So a bachelor student of Scott Aronson, who is one of the biggest ambassadors and scientists in quantum computing, she was challenged to prove that a classical computer cannot do the same thing as a quantum computer, that it cannot solve all these things with the same exponential speed up. And in a way, she failed terribly because she came up with a classical algorithm which does the same thing. And it was first for recommender system. There was a paper out in July 2018. Then for principal component analysis, and then matrix inversion for low-rank matrices, and so on. So suddenly it turns out that all of these magical conditions which allowed quantum computers to be more efficient also allowed classical or randomized algorithms to be more efficient. So the consequence of this was that exponential speedups are no longer a possibility. We could get polynomial speedups, but the degree that we could hope for was no longer clear. And in fact, the story is not done. I mean, it's from this year, 2023, they're continuously reducing the gap between classical and quantum algorithms, which are already no longer super polynomial. We're really talking about, I don't know, degree 3, 4, 5. Amazing things in practice, but not what I'm after. So this seems to be not the way to go towards these large systems, which is a shame, because it was an amazing time for me. But along this time, even though there was this murder in all of these various types of algorithms, one quantum algorithm from 2014 somehow survived, and that's the algorithm for topological data analysis. And the fact that it survived was the reason that I got interested in it in 2019, and pretty much like the story of Tank, I tasked my PhD student to dequantize it. Like Tank, he also failed because it proved that we cannot dequantize it. So this is really, at the moment, the sole survivor that I'm aware of this dequantization. So let me tell you about topological data analysis. Any experts on topological data analysis in the audience? If you are, you can go talk about it. Okay, so this is my way of presenting it. Please correct me if I say something which is really factually incorrect. So I think most of us will agree that machine learning is all about extracting robust features from data. Right? We don't want to learn noise. We want to learn the stuff which is really inside. So what I mean by that is that if you give me a point cloud and I would cover some data from it, some information, insights, if I were to rescale it or maybe rotate it or maybe continuously deform it a little bit, I would hope that my data analysis algorithm is robust under that. Right? Somehow it survives, the relevant information somehow survives. And if I start thinking about, well, what survives if I don't care about rescaling, don't care about rotating, don't care about the continuous transformations, what remains? What is the thing that I'm capturing from the data? And what remains is the so-called, I always forget this slide. So the point is a cat is a cat is a cat is a cat. Right? So if you have a cat, you know, they're deformed in various ways. Yet it's still a cat, right? What remains is the shape of data, or rather the topology. So you can imagine data living, you know, being sampled from some continuous manifold, some complicated object, which has topological properties, and this is the thing we're trying to abstract. So you can think of topological data analysis as a feature extraction method, right, which extracts topological features from point clouds. So let me tell you how this works. This is a part of the pipeline of topological data analysis. It is a complex, ever-growing field. It doesn't have one thing that we do, and this is not even a necessary step in all of them, but it's present in almost all of them. And it's the one that we care about quantumly, so this is what I'm emphasizing. So I have a point cloud. It's, you know, points in some ambient space, the dimension of which I don't particularly care about. And I want to understand the topology of this object. So topology, you know, connectivity, holes, and so on, this is something that I typically describe to objects of volume, not point clouds, right? So I have to turn this into something which can have holes to start with. So the way we do it is through this procedure where we first build a graph out of this object. So one way of building a graph is simply choosing a so-called filtration length, an epsilon, a value, a numerical value, and we decide to connect all the points which are within epsilon distance from each other. So now if you give me a point cloud, and I choose an epsilon, this generates a graph. And at that point, I can forget about the fact that this was in some Euclidean space. Now it's just a graph. A graph by itself is not yet the object that is this voluminous object that I want to think about. I want to use this graph to construct something which is called a simplicial complex. Simplicial complex, it's a complex of simplices. Simplices are lines, triangles, tetrahedra, and higher dimensional objects, which are generalizations of the pyramid, which indeed can have holes, right? They're full body objects or can have holes. The way we build such a simplicial complex on a graph is using something called a clique complex construction, where we simply define every clique, so complete subgraph of the graph, as a simplex in our simplicial complex. So a lot of unnecessarily complicated words, perhaps, but let's think about this. So if there's a triangle in my graph, this is a good counterexample. So if there's a triangle in my graph, this entire thing I will consider as a full object. It's not a hole. In this type of a construction, this thing cannot be a hole. However, this object here, which is not a triangle, can have a hole. And I can talk about dimensionality of these holes. So in particular, this hole I would say is one-dimensional hole. So loops are one-dimensional holes. Triangles, filled out squares, and so on have no holes. I can also have three-dimensional holes. I can have something which is like a three-dimensional object, which is hollow but has faces. That's going to be a two-dimensional hole, and so on. So the entire art of characterizing this object in terms of its topology, in fact, it's going to be in terms of its homology, is to count the number of k-dimensional holes this object has. So to this object, I can attribute a vector, where each entry is an integer, telling me how many holes of the corresponding dimension does my object have. So in this particular case, as I said, this thing here actually should be filled up. It has only one-dimensional hole, and I don't know how many two-dimensional holes it has. I didn't do the count. So I want to recover this vector. Right? This is going to be the features that I'm getting from data. And I want to do it in silico. I want to do it in a computer in some mathematical fancy way. And it turns out there's a piece of mathematics called Hodge theory, which gives me a linear algebraic way of doing this. So specifically, to this graph, I can, for each k, define a matrix, a linear operator called the kth combinatorial Laplacian. And this object talks about the connectivity of k plus 1 clicks. Now, just a quick reminder. The whole objects, the things which are filled up in the graph, are precisely the k clicks of the graph. So if a graph has, any subset of vertices of size k which is fully connected, that thing is a complete object. It's a k-dimensional filled up object. Okay? This combinatorial Laplacian is a generalization of the classical conventional graph Laplacian of graphs, which talks about connectivity of one clicks, of just vertices. So Laplacian is mathematical equivalent to the adjacency matrix. Adjacency matrix looks at the vertices of the graph and asks whether two vertices are connected. Yeah? The first combinatorial Laplacian, one level up, is going to look at all the edges. So these are the one clicks of the graph, and ask whether they're connected. I'm not telling you what it means for edges to be connected, but there's a notion of that. The next one is going to look at all the triangles in a graph and discuss whether the triangles are connected. Okay? So I'm going to have to go through all the triangles of this graph and figure out whether they're connected or not. So this is what the kth combinatorial Laplacian does for the kth click. Edge, triangle, tetrahedron, and so on. Okay? I will show you exactly how it's constructed in a second. Now, what's important is that it was proven that the number of k-dimensional holes, so the kth Betti number, that's what it's called, of a given graph is equal to the dimension of the kernel of the kth combinatorial Laplacian of the same graph. So if I can construct the kth combinatorial Laplacian and I look at the number of zero eigenvalues it has, this tells me the number of holes for my object. That's the mathematics that was proven in the last century, I can say now. And this is exactly how we'll play the game. Now, why is it interesting? Because getting topological data, topological information about data is interesting. Why is this interesting for quantum computing? Is because this is actually computationally hard. Now, why is it hard? Well, because this object here counts connectivity between k clicks. So the number of rows and columns that I have is the number of k clicks that my graph might have. And that thing is bounded by the combinatorial coefficient. So the number of k clicks is exponential if the size of the click that I care about, so the whole dimension that I care about, scales with the number of vertices of the graph. This has nothing to do with the dimension where the data was. This simply has to do with how connected my graph is. So the dimension of this object is very high. It's n choose k, if I care about k-dimensional holes. It is a Hermitian operator. You will see this in a second. It is sparse. It has logarithmically many non-zero entries in its rows and columns. And moreover, I can tell you can compute analytically where they are. You know where they are, you can evaluate them efficiently, which is what we call in computer science sparse access. So the objects which have a sparse structure, and hence you might expect much more efficient algorithms for this, especially quantum. So having something which is combinatorially large, Hermitian, and a sparse access, that is pretty much everything you could hope for in the context of quantum computing. And this is what we have in this case. So now the catch is, given that we know all of this, how do I compute the dimension of the kernel of such an object? So far so good? So, let me tell you how I put this in a computer, okay? So, here's a graph. It's in fact a clique over 5 vertices. And now I can represent on a quantum computer any subset of the vertices of the given graph. For instance, I will denote, you see they're labeled 1, 2, 3, 4, 5, so this vertex, this entry corresponds to this vertex, this entry to this one, and so on. So at 5 vertices, 5 qubits. And if I write 1, 1, 0, 0, 1, 1, 1, 0, 0, 0, what I mean by this is I'm interested in this particular clique of the graph. Okay? So this triangle here is selected by this indicator function. It's just the indicator function specifying the subset of the vertices of my graph. And for this particular graph, this bit string is a 3 clique. Because look, in the graph, all 3 vertices are connected, it's a clique. The same bit string in this graph is not a clique, because 1 and 3 are not connected. Okay? So not all bit strings are valid cliques of every graph. It's graph specific. If you have a complete graph, every bit string is a clique. And the Hamming weight of the bit string tells me the dimensionality, the size of the clique. Okay? Good. So now that we know this, I can define something called the boundary map, which maps k plus 1 cliques to k cliques. It goes from n k vertices or k plus 1 vertices to k vertices losing 1 vertex. How does it do it? If I put in a bit string here and I apply the k boundary map, what comes out is a formal sum, if you wish quantum mechanically superposition, of cliques which have 1, 1 less, 1, 1 fewer. So what does this symbol here mean? It means that I look at the bit string x and I set the jth bit to 0 no matter what it was. So if it was a 1, it becomes a 0. So this is kind of a weird thing. This one here is not graph specific. What it really does is it extracts boundaries from your whole objects. Imagine a tetrahedron, two-dimensional tetrahedron, which is just a triangle. What this map is going to do is it's going to give me a superposition of the edges. It's just going to be the 2 cliques that are present in this thing here. So it extracts the boundary, and this is why this thing is going to be able to tell us something about the holes of the graph. Now, this one here, this operator here is very easy to define. Like it's a very simple operator. It just puts in the jth position to 0, but it's not specific to the graph, right? In particular, this thing here is going to take an input something which is not a clique of the graph. So the way to make it specific to the graph is to simply sandwich it by a projection operator, which is going to send to 0 everything which is not a valid clique. So this thing here is simply a sum which goes over all the cliques that are actually present in the graph and send to 0 everything that is not. Now, this boundary operator here is well defined for this graph here. It only acts on the valid cliques of the graph. Okay? Now, once I know what a boundary operator is, this is a very simple matrix. This is your combinatorial Laplacian. So it has the Hermitian conjugate of the boundary map of k cliques and the Hermitian conjugate of the boundary maps of k plus 1 cliques. And if you look at the structure, you see immediately it's Hermitian no matter what. Right? It is del and del dagger and del dagger del for different indices, and it's summed up. Sum of Hermitian things is Hermitian. Each one of these things is in fact in positive semi-definite. And that's your boundary, that's your combinatorial Laplacian. That's it. Just to remind you. So this thing simply looks at the cliques and sets to 0 the ones sequentially, one at a time. This thing here just sends to 0 everything which is not a valid clique in your graph. And I just sum it up like this. This gives me my combinatorial Laplacian. It's a very, very simple object, but still combinatorially large in the size of the graph if I care about high dimensional holes. So now I want to compute the dimension of the kernel of this thing on a quantum computer. And this is, yes, thank you.
Very short understanding question. These 4 formulas, have they still something to do with the 2 figures, or is it just one?
No, I mean, this is the general expression for the combinatorial Laplacian.
So it's not that this is for figure 1 and this is for figure 2?
No. Sorry, this is independent. But what is important to keep in mind that the graph is not complete. Like the graph that I get from data is typically not complete unless my epsilon is 1. Okay? I have to worry about the fact that not all cliques are valid cliques. It's going to be a huge headache for me, forever, for the rest of my life. So I want it to be a headache for you as well. Not everything is connected. Okay, so let me tell you now how Lloyd Garneron as an artist figured out how to compute dimensions of kernels on a quantum computer using, name your 3 most easy to remember quantum algorithms, and those 3 are the ones that I used, essentially. In fact, maybe even. So this is quantum computing 101. Every course is going to cover this. I'm going to just be using 2 quantum algorithms. One is simultaneous simulation, the other one is quantum phase estimation. Again, over Uza, I'll be happy to give you details how these algorithms work, but I'll tell you what they do right now. So let H be a Hermitian operator in the physics vernacular, the Hamiltonian. And let's suppose I have sparse access to it. So I know where the non-zero elements are, I can compute them. For the physics, maybe I tell you what the poly decomposition of the thing is, okay? So if I have this Hamiltonian, there's an algorithm called Hamiltonian simulation, which allows me to apply the operation xiht for a desired t onto a quantum register. So this thing here is a unitary. There's a relationship between the Lie algebra here, and this is in the Lie group, but let's not do the fancy math. You can just prove that if this is summation, this thing is unitary, and for any unitary there exists a generating Hamiltonian such that this equation works. Okay, what is important to know is that these two guys have the same eigenvectors. They don't have the same eigenvalues, but the eigenvalues are intimately related. In particular, if lambda is an eigenvalue of this guy, e to the I lambda t is an eigenvalue of this guy. And if I understand this thing, eigenvalues of this thing as, you know, complex numbers with just have a phase, the angle in the Cartesian plane, then the eigenvalues become the eigenphases of this operator here. What does quantum phase estimation do? If you give me black box access to a unitary of this type, and its powers, and it's controlled, let's ignore the details right now, and if you give me an eigenvector of this operator here, it can tell me what the corresponding eigenphase is. That's what it does. So you apply this operator in a certain way onto the initial state, which is initialized in an eigenvector of this operator here, and what you read out is the binary specification of the eigenphase. Okay? Eigenphase of this guy is the eigenvalue of this guy, call it lambda. So let's plug in here the random eigenvector of this operator here. So what comes out is a uniformly at random sampled eigenvalue. So I check, is it 0 or is it not 0? If it's 0, I increase the counter. If it's not 0, I don't increase the counter. I do this 78,000 times. I divide the number of zeros I see with the number of samples, and that's a good estimate of the dimension of the kernel. Because the kernel is nothing but the number of zero eigenvalues. I don't get it directly, I get the ratio. So technically speaking, I get the normalized dimension of the kernel because it's divided by the total dimension of the operator. That's it. These two algorithms just give me a random sample of either. Now, I want to do this for combinatorial Laplacians, and I want to do this in general. Is anybody bothered by something here? Everything fine? You can do it? You're not bothered because that doesn't mean anything to you. Just wait. So for the quantum people, if I ask you, so here's a Hamiltonian, please prepare a random eigenvector of that Hamiltonian. How are you going to do that? How do you prepare a random eigenvector over a given Hamiltonian? You can't. You cannot without diagonalizing it. You would have to find the eigenvalues. This, in fact, is a good idea, but it's not going to work because I don't know how to generate random eigenvectors. But here's the thing which Lloyd Garneron has not figured out. I don't actually need that because I'm plugging in here is really a random eigenvector. Mathematically speaking, this is a maximally mixed state over the entire Hilbert space. And maximally mixed states have resolutions with respect to any eigenbasis, including the computational eigenbasis that I know. So it turns out, mathematically speaking, that this entire computation is going to give me the same expectation value, the same numbers out, if I plug in here random eigenvectors of H or any other random basis states. It is simply mathematically the same object. So it turns out I don't need to know the spectral decomposition of H. I don't need to know its eigenvectors. I just plug in random stuff, and what comes out is the right expectation value. So now suddenly it seems like I can do this particular thing. And now, I mean, at this point, everything else becomes technical details which maybe you don't care about, and maybe I don't want to bother you with them. I will go relatively quickly through them. But this is the main idea. I mean, this works as long as I have a Hamiltonian here, but I told you that the combinatorial Laplacian is a Hermitian operator that I can compute the entries of. So I can run Hamiltonian simulation on this thing. I can plug in random eigenvectors. I can see if the eigenvalue is 0 or not, count the occurrences, and this gives me the frequency of the 0 eigenvalue. Okay? Technical details, how it's actually better to not actually do the combinatorial Laplacian. I will skip this because I don't think it's very, very important for you right now. It will happen, and here I will have to be careful, is that again, I don't have all the edges in my graph. Not every click is a valid click. You remember that? I made a point. Not every click is a valid click. That's actually a problem. That means that my combinatorial Laplacian is technically speaking not really acting on the whole Hilbert space. It's only acting on the part of the Hilbert space spanned by the valid clicks of the graph it represents. So the way to do it is to prepare the initial state not in a random eigenvector, which would be a random choice of the whole Hilbert space. I have to prepare it just in the part of the Hilbert space which is spanned by the valid clicks of the graph. Not a problem. I just take a random click of the graph and plug that in. It turns out that works. That's fine. All I need is to find a random click in the graph. Anybody worried now? You never had to find a random click. How difficult is it to find the largest click in the graph? So I'll give you a graph, then a genesis matrix. How quickly can you find the largest click? Is there a click of size 72 in your graph? Let's look at that decision problem. Or maybe let's look at the complement graph. Let's look at the largest maximal independent set. I'll tell you in a second. So these are the technical details. But this is what we want to do. So quantumly, why are we so happy? Because quantumly, this Hamiltonian simulation turns out to only scale low polynomially with the number of vertices of my graph. Everything here, all the other steps seem to be cheap and efficient. I have to choose a random click. Classically, on a classical computer, if I want to solve the same problem, if I want to estimate the dimension of the kernel, the best procedures that we have, this is no longer true, it was true a year ago, I'll correct it in a second, scale is n to the k. If I care about k-dimensional holes, I need to diagonalize a matrix of this size in general. And now if my k scales with n, this is strictly exponential in the number of vertices. Polynomial, exponential. Woo! We're super happy, right? Maximal independent set, max click, is one of the 21 carbs NP complete problems. So this little step here, which I just said, well, we just get a random click, you can't do that, not in polynomial time. It's a classical bottleneck, and it turns out to be a fundamental bottleneck we don't know how to circumvent in general. So this entire quantum algorithm only works when this step is somehow efficient. And that ends up being a super significant restriction. So we only know how to make these things work if my graph is dense. Meaning it has most of the edges, and then if I randomly choose a subset of vertices with high probability, or rather not exponentially low probability, that thing is a valid click in the graph. Then we know how to do it. Operatively, what that means is that in my topological data analysis pipeline, I have to choose a large epsilon. I have to allow faraway vertices to be connected, then the graph becomes dense enough. Now, this is a very worrisome point, right? Because I said classically, this is the runtime, but what if I'm only interested in a very densely connected graph? Maybe there's a much more efficient classical algorithm in that case. Maybe, but turns out nobody figured it out yet. So there's still a separation for this regime, even though we're not super happy because PDA tends to like your epsilon to be scalable, to choose it wherever you wish. There's other details. Another detail is that quantumly, I get this normalized Letty number, and I hope to be able to tell you a few sentences about why this matters. That is, I get the number of holes divided by the total number of k clicks. That's the thing that the algorithm estimates. Whereas classically, I get the actual Letty number. Not clear whether I care about that. Not sure, but these two things are not the same. Classical algorithm is required to do more, or actually gives me more for free. And because of details, a number of questions emerge. So maybe to put things in perspective, the paper of Lloyd Ganarones and Ardi came out in 2014. We started looking at this in 2018-19, and in the meantime, there were no papers on this topic for reasons that are not clear to me. And then suddenly you will see there's been, I don't know, 10 papers out in a short period of time, including with the colleagues in IBM from Africa, in fact, and many others who tried worrying about these questions here. So question number one was whether we can dequantize it, whether these U and Tang type techniques can be applied to the topological data analysis case, whether we can improve the quantum algorithm, which has this bottleneck of click sampling, at least that bottleneck, whether it has more interesting application than what I just showed you. Why would you care about more interesting things? It's the most interesting thing in the universe. And whether it actually matters. So this is going to require a few more details that are latest paper on the topic. So let's start very quickly fleshing out these results. So in 2020, we showed that a generalization of the topological data analysis problem, where the Hamiltonian is not just a combinatorial Laplacian, but it's allowed to be a more general object, that thing is DQC1 hard. What is DQC1? It's a subclass of quantum computations. It's a set of decision problems that can be solved with so-called one-plane qubit model. So BQP, the class of problems solved on a quantum computer, says start with initial register in an all zero state. So every qubit is in a perfect zero state. Apply whatever unitary you wish. Measure the first qubit and find out whether the qubit outputs a 0 or a 1 with probability higher or lower than, let's say, 2/3. Okay? That is the quintessential problem of BQP. The DQC1 model doesn't start with an all zero states. It has one qubit in a zero state and everything else is in a maximum unique state. It's a restricted model of computation. We can simulate it in a full-blown quantum computing, and we don't know how to do everything we would like to do with this model here. But very smart people tell me that this thing is beyond the scope of what classical computers can do. Peter Short says he doesn't know how to dequantize it, so we all believe Peter Short because he's never ever wrong. Anyway, but now in all seriousness, nobody is really trying to dequantize DQC1. Nobody really thinks that this is going to happen any more likely that quantum computers are going to be fully dequantized. So if this word generalization wasn't here, I would be very confident telling you we can never dequantize the topological data analysis algorithm. It is really an ironclad separation. However, our generalizations are actually quite more general, so I'm just moderately confident. I'm a little bit happier since recent times because some very smart people have really tried, and they've invented ever better classical algorithms that use the structure of topological data analysis, and it still falls short. Still there's an exponential separation. What we get and they get, at least in some regimes. So, I don't know, we'll see. We'll see what happens. Second question, can I improve it? Can I get away without doing that sampling thing? Almost certainly not. So what was proven by Marcus Luquinho and others is that estimating Betty numbers up to multiplicative precision, which is what our algorithm does, or tries to do, is QMA1 hard. So this class here, let's just put it this way, it contains NP. It almost certainly strictly contains NP. So it's even harder than NP hard problems. There's a conjecture that for combinatorial Laplacians where the smallest eigenvalue, which is non-zero, is not more than 1 over polysmall, that in fact the problem is QMA complete. That would be a fantastically weird thing, a very, very important thing, because it would be the first example of a natural problem which is exactly capturing the types of things quantum computers can verify. So every other problem that we know, which is captured by the class QMA, is inherently a quantum problem. Topological data analysis doesn't look inherently quantum. It really looks like a classical problem which is fully capturing this class. 2 slides from now, I'll tell you that in fact it is a quantum problem in a very strange way. Okay, but so far this is kind of a cool result. We're waiting for these guys to actually find it. They're promising to do it for a while now. We'll see what happens. So we don't think we can actually generically improve the thing. Can we do more than just topological data analysis? Yes, you can do complex network analysis. You can do things like estimate the Rényi entropy of matrices which end up being combinatorial Laplacians of large networks. Those things capture certain properties of connectivity of these graphs. And instead of just looking at the number of holes, you can look at the entropy of this thing, which gives you exactly the same kinds of separations as counting holes. Question 4. Is there anything more which is not related to topological data analysis? There's a funky connection by Ed Witten from, I think this is actually incorrect. I think this is 1989, but I'll stick with 82 for now. Ed Witten proved a one-to-one relationship between a special type of quantum mechanical theory called supersymmetric quantum mechanical theory, which means that the Hamiltonian is in fact given by a so-called supercharge operator. So this is just the anti-commutator. It's Q dagger minus, plus Q dagger Q. That's what defines the supersymmetric quantum mechanical theory. This thing is in one-to-one correspondence with the combinatorial Laplacian. It is the combinatorial Laplacian. In other words, supersymmetric quantum mechanical theories uniquely fix a data set. And every data set fixes one supersymmetric theory. And computing properties of the supersymmetric theories, in particular the number of ground states, is exactly the same as counting the number of holes. So in some sense, topological data analysis ends up being very much quantum mechanical. And it's the kind of quantum mechanics that we don't even think is the, well, we're not sure whether the real world is supersymmetric. So it's kind of a funny connection. So this one I'll skip. And the last question has to do with whether this topological data analysis business, once I really take into account all of these details that I mentioned, does it actually have a chance of giving any sort of an advantage in any particular case in, let's say, first generation of fault-tolerant quantum computers? So this requires really being fully precise. And this is what we did with our collaborators from Google. We're interested not in near-term applications, but these fault-tolerant ones. And our job was to really see whether these things can work out. So let me tell you what our main finding was. So we improved the algorithm in absolutely all parameters to get the smallest numbers possible. And what we wanted to do is count the expensive operations of the algorithm. And we end up with such a cost. You've probably seen complexity analysis of some algorithm. And you will note that usually here there's a big O, right? There's no big O because this is almost exactly the number we get. It's not the asymptotic number. It is the actual costing of the algorithm, because we care about precise numbers. So this took a little while. Well, I'm omitting many terms which are very small, but it's not an asymptotic statement. It's the actual statement. And we find that the quantum algorithm is dominated, the cost of the quantum algorithm is dominated by this term here, by the kth binomial coefficient divided by the actual Bethe number. So if the Bethe number is small, the cost is larger. If the Bethe number is larger, the cost is small. Okay? Now, classically, I told you that in the worst case, you have to diagonalize the matrix. The matrix is of this size, so let's say that's the cost of the classical algorithm. So classical algorithm costs n choose k. Quantum algorithm costs square root n choose k divided by the Bethe number. So if I want a high degree quantum speed up, this better be large, and this better be small. So the question becomes, are there actually graphs which have large clique numbers, so such that this is large, but are still Bethe dense? Now, I mean, parameters, I can put in whatever numbers I want here, but these numbers have to come from my graph. So if my graph is large in clique numbers, then it means very dense. It has a lot of edges. But if it has a lot of edges, then it doesn't have a lot of holes, right? Because if I have a hole and I put in an edge, it's no longer a hole. So there's a tension here. There's a tension between wanting to have a lot of holes and wanting to have a lot of cliques. And it was not clear whether this can ever work, right? Whether there's any situation in which this thing works. And then we analyzed it, and we're not the only group that did. We know that for the regime where k, so that's the dimension of the hole, doesn't scale, then we cannot have a superpolynomial separation because the classical algorithm has a polynomial like that. It's n to the k, if k is constant, it's just a polynomial. So that's not going to work. What about having k scale proportionally with n? Let's say 1/10 of the number of vertices, right? So we analyzed this problem, and we looked at a family of so-called extremal graphs, which maximize the number of holes you can get. And we find out that the Bethe number is not large enough. It's not detectable in polynomial time per hour algorithm. So it seems like a no-go. So what really happens is we can get whatever polynomial speed if you wish, but the quantum algorithm is not efficient. It has an exponential runtime itself. So it is a speed up of whatever degree you want, but the quantum algorithm is still too slow for practical use. And this is where I think most of the analysis ended, except it went for just one more question, just one. What happens when k scales fully logarithmically with n? And here we got lucky, and things conspire that for this family of these extremal graphs, it turns out that the classical runtime is now n to the log n. Note the exponent grows, so this grows faster than any polynomial, whereas quantum will get a strict polynomial runtime. And that's the superpolynomial separation that was not clear existed. But now we know it does, at least for this family of graphs and things which are small perturbations there. And we wanted to see, okay, so how big does the instance have to be such that we really have some kind of a speed up? So we played around with actual numbers. And if you consider a graph of 256 vertices and you care about 16-dimensional holes, we get an effective 7.5 power speed up. The number of clicks is 10 to the 19. That's the classical cost. And in this case, we're considering it as memory. Right? There is no supercomputer which has this amount of memory. That's what's preventing classical computers from doing it. Quantumly, we require 80 billion expensive operations, which if you do the math, and if experimentalists don't lie too much, if a quantum computer is ever built, this would be anything between 3 days and 3 weeks of computation. And this would be an example of something that classical computers really cannot do because you cannot even fit it in memory, let alone compute anything. And the instances are not too large. Similar numbers are seen in some prognosis of what happens in quantum chemistry. So it turns out topological data analysis has sort of the same requirements in terms of quantum compute power to have real-world advantages as quantum chemistry does. But it's a completely different problem. And with this, I'm absolutely out of time. But I want to tell you that topological data analysis is a relatively new branch. It's not very well explored because it's expensive, because it has a high degree polynomial runtime whenever you start counting high-dimensional holes. But you can find a bunch of papers in neuroscience, genetics. So neuroscience is mostly brain imaging. They're trying to understand the connectivity of your brain under FNMR experiments. In genetics, it's phylogenetics of Dario Reri of the zebrafish. In material sciences, that's the only one of 2 papers here where they actually went to 3-dimensional holes to understand what's happening in certain there's some paramagnets, I don't know what they are. Public health was the spread of Zika virus. It's more of a network analysis type of thing. Economy, critical situations, like predicting like the 2007-2009 collapse, apparently could have been done if something topological data analysis. We're playing around with high energy physics as a potential application because of the connection to supersymmetry. So yeah, so it's been applied, but not in the regimes where quantum computers really shine, where K is large, because you cannot run it, right? So it's that's sort of the fact. So I just want to add end with this slide. TDA is cool. It's an extremely cool thing. It connects to homology theory, which is very intimately connected to computational topology and homotopy theory, which is as deep as you want. It seems to be an interesting new way of analyzing data. It is the only known survivor of the U-intent dequantization era for superpolynomial speedups. It seems to be really capturing the most quantum essence in terms of complexity theory. It seems to be connected to supersymmetric theories, and it's not out of the question to be one of the first applications of quantum computers with an advantage. So, I mean, yeah, anyway, it's as if topology is well connected. And with this, I will end. I would like to thank all of the co-authors on these papers that we did. And I would like to remind you that there's another thing that I wanted to talk about, which is provable learning separations, but that's so thank you.
Good evening. Questions?
Very naive question, really. Does this collectiveness has anything to do with the entanglement, or is it completely separated?
Okay, certainly the topology of the graph and the connectedness is going to influence the quantum operations we apply, and it will influence how much entanglement is generated in the computational process. That will be one of the reasons why you cannot classically simulate the quantum algorithm. So very indirectly, certainly, in any more direct way, I do not know unless your data comes from measuring the quantum system, which is highly limited. It's the best I can do on the spot.
Okay, thank you.
In the case of the financial crisis in 2008, the crisis itself would have been a hole or a
So the way that these very optimistic papers describe the situation is they look at time series data of a bunch of parameters and identify different type of connectivity of one-dimensional holes pre-crisis and right before the crisis. In other words, if you had done topological data analysis and you had the right classifier to detect the signature, then you could have identified that particular crisis. So I think that's a true statement, that everything else is conjectural.
So these high-dimensional holes and these applications that you mentioned, are they really looking for high-dimensional holes? Because now you said like they're looking for one dimension, right? They're
So none of these papers that I looked at, I spent some time even this morning going through them. One neuroscience paper, this materials paper, stuff they do in high energy, they go to dimension 3.
This is because it's not possible.
Yeah, at that point it becomes intractable. I mean, it simply takes too long to get anything out of
We
it.
don't know whether it will be useful because it's just not possible yet.
We have evidence that it should be useful. We know for a fact that certain properties cannot be captured by lower dimensional connectivity, but whether or not these are the things which really govern our world, I don't know.
So it's really the limit that classical.
That people have been trying. At 4, it becomes, I mean, at 4 you would have to start putting things on a cluster, and then the question is why? Why are you putting it in a cluster? Now we have a reason to, because quantum computers would be better, right? But beforehand, it was not necessary to do that.
Then in order to compute the persistence diagrams, don't have to compute as many, yeah, you know what I mean. Yes.
I mean, to compute persistence, okay, so, okay.
Then I need all the Bethe numbers.
Well, you need all the buttons. Moreover, you need
in material science, so if it is true that I need as many Bethe numbers as possible to compute the persistence diagrams, then the material science application is classified.
But you can look at persistent diagrams just for 0, 1, and 2-dimensional holes. They're persistent.
That's
So
what you can do?
Okay. But I mean, persistent diagrams. So persistent diagrams come out when you study what's happening with your holes as you tweak epsilon. That's a very important thing because you don't know at a given epsilon whether the holes are real or simply a byproduct of data processing. But the holes that persist at various filtrations are more likely being inherent. Okay, there's deep mathematics why this is the case. So you want to tweak epsilon, which is bad for me because I cannot, right? I have a limit. When the epsilon becomes too small, the things become intractable. So that's a separate issue.
Other questions?
Different role. You said you are hiring pre-docs to postdocs. What are you expecting from them? Computer science, physics, mathematicians?
That's the thing. We have, so the applied quantum algorithms team has, I would say 40% physics, 45% computer science, and the rest are chemists. Online, we have one mathematician. I like mathematicians, but they typically want to do smarter things.
Okay, thank you very much.
Thank you.
Quick remark, so the time of the user reception is really at 7 p.m. Right? Johanna changed the program to 7 p.m. down at the beach bar. Right?
It's different to the printed program.
Okay?
So not like in the printed program, which I see.
Johanna changed it. Online is not the right time. Online, the online program says the right time, 7 p.m. 7 p.m. So we reconvene at in 12 minutes. Yeah.